displacements had to move along the constrained surface. They had to move along the lift floor. Why? If I allowed some virtual displacement that would come outside of the lift, well, it would no longer be at right angles to the normal force. So it would, the normal force would now be doing virtual work. If I allowed the virtual displacement to come out of the lift, if I allowed them to violate the constraints, this would no longer be true. I would no longer be able to say that they did the normal force, that the constraint forces did no net virtual work. It would no longer hold. And then I still have these FIC, the constraint forces, in my equations. So we have to say that the virtual displacement, when we pause the system, must move along the constraints. Along the constraints, that they must be feasible. They must be feasible. Alright. So this equation that we derived, the Allenby's principle, it holds for any virtual displacement that is feasible. Doesn't hold for any possible little motion of all particles. It holds for those motions that are feasible. Those that move along the constrained surfaces. Those for which the block moves down the slope and not through it. Those for which the particle moves in the lift and not below it or above it. Those are the situations for which it holds. So, there are holonomic constraints, our standard equations of constraint, relating these delta Ri to each other. So, this equation holds for all feasible delta Ri. What does that mean? For all delta Ri, for all little virtual displacements, that satisfy the holonomic constraints of my system. Okay, that means I cannot simply choose these to be absolutely anything. I cannot, for instance, choose them so that the x component is 1 and the y and z or the other components of 0. If I could do that, then I could make it so that these sums disappear. And I would have real equations, local equations that don't require us to sum things up. That's where we go. That's where we head. But we can't do it now, because these guys are related by constraints. And we're finally going to get rid of these buggers. We're going to do it by transforming to generalized coordinates. So I've written up here this theorem, this principle, the Allenby's principle. And our program for this lecture is essentially going to be to take that thing, transform it to generalized coordinates. And there are a couple of identities that we'll need to make our sailing more smooth. Otherwise, at some point, we'll be doing very hairy mathematics. So we're going to derive a few little random identities. What I want you to do is, I would have left the identities on the board, but unfortunately we can't because the hurricane struck here last night and it's caused a little bit of wreckage. So I'm going to derive them. I'm going to ask you to write them down. Right? Get out another piece of paper. If you want to copy down my derivations, that's fine. But I'm going to put boxes around the important things. Write those things down. Have them in front of you. I would have put them on the board, but I can't leave them there now. Have them there. Have them accessible. So we're going to derive a few identities. The first one's the chain rule. The chain rule is pretty obvious, right? Now, when we transform from Cartesian coordinates to my generalized coordinates, I can write the ith particle position as a function of my generalized coordinates. And time. Right? In the case of the moving lift, the generalized coordinates aren't left, the x and y. I also need to know time. Time will then tell me how high up everything is. Right, so sometimes there's an explicit time dependence, sometimes there isn't. These are my general transformation equations, right? My x is equal to r cos theta, y is equal to r sin theta, or whatever. They're my transformation equations. Alright. What happens when I differentiate this with respect to time? What happens if I differentiate? Let me not even think about this as necessarily my positions. Let me think of any function of these things. What happens when I differentiate that with respect to time? We use the chain rule. df by dt is the sum over j, right? J from 1 to n of del f by del qj dqj by dt plus, don't forget the last parameter, del f by del t dt by dt. I simply use the chain rule here, right? If I differentiate f with respect to something, I must go through all the things f depends on, take the part of f in that direction, so to speak, bit of f that is in that component, and times it by the derivative of that component with the something that I differentiate. And that includes time. So let's simplify this. dqj dt I'm going to simply write as qj dot. Right? So I can write this as the sum to j is 1 to n of del f by del qj times qj dot. Right? Plus, what's dt by dt? 1. So this is just del f by del t times 1. Right? This is in brackets. In case you were wondering. Right. So, in particular, I'm going to use this relation to derive the other relations, but it's not quite a thing to put in a box yet. In particular, I'm going to now apply it to position Ri, right? Ri, the ith position, is one such function of my generalized coordinates, right? That's called the transformation equations. I can get the position of the ith particle as a function of my generalized coordinates. So, I can write dri dt what is dri dt, otherwise known as? The time derivative of position is velocity. So I'm going to also just write this as vi is equal to, well, we simply replace f with ri here, because ri is itself a function of these guys. So if I want to differentiate it with respect to time, I do this, right? And I get the sum j 1 to n of del f, not f anymore, f is ri. So ri by del qj dot plus del f is ri, del ri del t. Right, so that's the expression for velocity, and that's the first thing I would like to box. Box it, call it 1. You're going to use it. Okay. We're going to make a really, really simple deduction from that now, which we'll also use. Let's take the partial derivative of vi, the ith velocity, with respect to qj dot. How do you take a partial derivative of something? Well, you look at it. What's the derivative of this thing with respect to qj dot? Well, it's not a function of qj dot. It's a function of the qj's and of t. So the derivative of this term with respect to qj dot is 0. What's the derivative of this term with respect to qj dot? Well, 1, right? 1 if j is equal to I and 0 otherwise, right? So it's 1 only for one term in that sum. What's the derivative of this term with respect to qj dot? Same story as before. It's a function of the positions, but not of the velocities, yeah? Not of the generalized velocity. So again, it's 0. 0 delta is just with respect to k delta j k and 0, right? When I say delta j k, I just mean it's only going to be 1 if j is equal to k. Del qj dot by del qk dot 1 if it is. So when I write all of that out, I'm only going to get one term out. Right? It's going to be 1 for one case. And we're going to have whatever remains, and that is del Ri by del Qk. What was 1 2? Right. Yeah. Right, so this thing here is a function of what? Del R by del Qj. What is it a function of? When I took R was a function of the Q's, and I differentiate with respect to Q. What is it now? It's a function of Q's. And T. It's not a function of Q dot, correct? It's not a function of Q1 dot or Q2 dot, it's a function of Q1 and Q2. If I take the partial derivative of this thing with respect to Q something dot, it's 0. It's not a function of that thing. Same with this one. R was a function of the positions and of time. If I take a derivative of R, of this thing here, with respect to Qj dot, not a function of Qj dot. That's 0. It just goes away. The only term that is possibly a function of Qj dot is Qj dot. That is a function of Qj dot. Right? That is a very simple function. If I differentiate this with respect to Qj dot, I get 1. But if I differentiate it with respect to something other than J, Qk dot, I get 0. Just like differentiating x with respect to y partial into 0. So this will only give me 1 when J is equal to k. And when this gives me 1, right, then what's left is that 2. That's what comes down here. Make sense? Right, it's in the notes.
So the only element will be left there is with respect to
Is the k, that's right. All the other things in the sum are going to be 0. Correct. Very good. So, we've got two relationships, two little identities now. Now we're going to, well, how we're on a roll, let's differentiate this guy with respect to time. Just because we can for now. We'll see where it comes from later. Differentiating this guy with respect to time. What is this guy a function of? It's a function of these things. Just like it. So we differentiate with respect to time the same way we differentiate f with respect to time. d by dt of del Ri by del Qk is equal to, wow, same story, right? Well, sum over j. Sum over j. I'm not going to write the limits on the sum, and we all know j goes from 1 to m. So we sum over j, del f by del qj, qj dot, plus del f by del t. What's f? F is this thing. So it's del by del qj of f, qj dot, plus del by del t of f, right? All I've written is this thing. Now I'm going to substitute for f. F in this case is del Ri del Qk. Right. And we're all okay up to there. I'm going to rewrite these things. This is the second order partial derivative, right? It can be written in the other way around. I can swap the order of my differentiation when I'm doing a second order partial derivative. That's called, I never know the name of it, Clairaut's theorem or something. It's not important. We all know that it's true, right? For C1 continuously differentiable functions, you can do this. You can swap the order of partial differentiation. So, just to be clear, right? This thing here can be written as del squared Ri by del Qj del Qk. Right? And I can swap the order. I can say del Qk del Qj. The same thing here. This one can be written as del squared Ri by del Qk del T del Qk. And I can swap the order. I can go del qk del t. Why did I do that? Well, there's a del by del qk in common everywhere here. Right? Del by del qk, del by del qk. So I can write the second order derivative by taking a del by del qk out again. Del by del qk, I've just taken a different one out. Times del ri by del t. And here again, I can take out the del by del qk. Del ri by del qk. Right, it's just a bit of manipulation. It's nothing special. All I've done is I've looked at them. They were second order mixed partial derivatives. I can swap the order of differentiation, and then I can take out one of my differentiation operators. Well, this guy can just about come outside of everything, right? So let me in fact take him outside of my whole sum. Right? The sum's not dependent on k. It's a j thing, right? So this k can come out. Right, well, what's this thing? Anybody can tell me what this is? Looking there. But what's f there in this case? Is it r? Yeah, it's r. So, alright, in fact. This is del by del qk of del by del qk of the thing inside the bracket. The thing inside the bracket was dfdt, correct? And f was ri. Right. So what have we shown? We've shown that d by dt del ri del by del qk is del by del qk del ri del dri dt. Right? So the full and the partial derivatives themselves are mixing here. The ri dt is a special thing. What is it? Time derivative of the position. Right, so in complete summary, something to be written in a box. The left-hand side is d by dt of del ri del qk the right-hand side is del vi del qk. We'll put a 3 next to that box. Okay, I'm going to derive, get rid of this. All in the notes, and you want the results. Right, so we derived a couple of identities. One particular thing we're going to want to transform is these little delta ri's, right? We need to transform them. So let's write down that, how that transforms. Remember that I specifically stated when I talked about delta ri, virtual displacement. I specifically mentioned that it was independent of time. No time dependence. Now what does the chain rule tell me for a real displacement? For a real displacement, it tells me, well, dri dt, we already know how to do this, right? It's this equation up here, right? I'm not going to rewrite it. I'm simply going to multiply everything by dt. dri, a real displacement, everything here multiplied by dt, so I can take the dt away there, qj dot can be thought of dqj by dt, and I can get rid of the dt, and see what happens. So this looks like sum from j, 1 to n of del ri by del qj dqj plus del ri del t dt. Yeah, something multiplied everything by dt inside this. Okay, that's a real displacement. But I specifically stated that a virtual displacement is done at an instant in time. So for a virtual displacement, They transform similarly. But what happens here? It's a virtual displacement. It's done independently of time. There's no time dependent. So that's our transform. Right. So that one we'll call for. We'll transform our virtual displacement. Those are all the identities we're going to use. These have those excesses. Now we're going to embark upon actually transforming these results, the Deriving principle, into generalized coordinates. And we're going to do it by essentially transforming the left-hand side and the right-hand side, and then when we're done, saying they're equal. So let's do the left-hand side. Okay, for the left-hand side, let's transform delta Ri. We know how to transform delta Ri. Identity 4. So we're going to do it. Sum over I, I'm writing out the left-hand side. Fi dot. Delta Ri is a different thing now. Delta Ri is sum over j of these guys, right? Del Ri, del Qj, delta Qj. Right. So that is the left-hand side. Let's think about this a little bit. Let's play with this equation. Well, I can put the sums together, right? I mean, there's no need to put the sum of the j and the sum of the I separately. I can take them out and I can put the sum of the j on this side, right? There's nothing wrong with that. So now I have Fi dot delta Ri dot Qj times delta Qj, right? But now we notice that in fact all of this stuff is dependent on I, and this stuff is not, right? This is j dependent. So that whole sum can be thought of as occurring and producing one entity which sits inside this sum, right? Fi dot del Ri del Qj, summed up over the i's. Now, if you're very clever and you've read all your work and you've got an oral test with me tomorrow and you've really thought about the stuff, you'll be jumping up and down at this point on your feet and saying, with this is a tangent vector. And we're simply dotting f with a tangent vector. This whole thing can be written as f dot the j tangent vector, right, of the transformation. So if you're very quick on your feet and you've seen this, then get yourself quick around the sword. Otherwise, we'll carry on. So we've got a j. This guy here we think of as f dot ej times delta q. F dot ej, it's just notation, right? When I say f dot ej, I mean that. And it's also known as qj. Remember, we did this in polar coordinates. We had qr and q theta. The generalized covariant components of force in the j direction. So, in short, I can write this whole thing out as the sum over j of qj delta. So that's all that happens when we transform the left-hand side. I'm going to take this for away. This is all that happens when we transform the left-hand side. The left-hand side becomes qj delta qj, where this big qj is a generalized component of force in the j direction, and can be computed by doing this. Hey, you might say that was easy. Why did we derive all those hard-looking things that was so easy? This is why. The right-hand side. We're going to start the same way. How do we start here? We change delta Ri into delta Qj. We'll do the same thing here. We'll change delta Ri into delta Qj. So, the right-hand side can be written as a sum over I mi ai dot delta ri, right? And so you already know that I can write this as a sum over j ri qj qj. Okay, so that's the same thing we did here. And the same like we did here, the sum over j can come out. So the same like we did here, we take the sum over j and just move it front. And the same like we did here, we now realize that this is something times by delta qj. Correct? Okay, but this something is annoying. We have to think about how to transform. So it's mi ai dot del ri dot qj that we really have to think about how to transform. I'm going to raise these. I hope you've got them written down. Right here. So, it's got all these identities, and we're now going to transform this inner part. This is a place where we're essentially so I'm just going to consider this piece inside both sums, right? For convenience, just for notation's sake, let me call this alpha I j. It's dependent on I and j, right? It's just some quantity, so that I can write alpha ij is equal to mi ai dot del ri by del qj, and the right hand side is written as the sum over j of alpha ij delta qj. Right. Oh, sum over I and j of alpha ij delta qj. Right. So that's the right hand side. We just look at it there. Alpha ij is just the piece inside. We're going to want to transform this. So I'm just kind of focusing our attention in on this guy. Now, first leap of brilliant French mathematics. Right? So Lagrange was the guy who was working on this. And we can kind of see a step up, right? We had Bernoulli thinking about things conceptually. We had D'Alembert thinking about things conceptually. But Lagrange was a genius. We'll see why now. He was different from the others. This thing here just looks like a piece of equation. Well, we're going to think about it cleverly. The first thing we're going to do is we're going to say, I want to take out a time derivative. So I'm randomly going to decide to write out the following product rule. What is the time derivative of mi vi dot del ri del qj? Okay? I use the product rule here. The first thing I do is differentiate the first term, and then I differentiate the second term. When I differentiate the first term, I get this, right? So let's write it out. Equals, well, it's equal to mi ai, when I differentiate vi, dot del ri by del qj, plus, it's a product rule, I differentiated that, now I must differentiate this, mi vi dot d by dt of del ri by del qj. Right. So this is alpha ij. This is a time derivative of something. And this is another term. So we can rewrite alpha ij then by rearranging this equation above.